Hey scientific minded people, welcome to yet another video by Pale Blue Thoughts. Today I hope to conclude the series on the bird's eye view of the universe and move on to other interesting things. But can we close the chapter without telling how the Earth was formed when we are talking about the solar system? After all, it is our only home. Wouldn't you like to know how it came into being? Also, I got a few queries asking, why do planets keep spinning all the time? Why can't they travel without spinning about their own axis? I mean, gravity makes things revolve, but what makes things rotate? And to conclude the video, we will spread our wings outside our solar system and look at our solar system from outside of it. I'm sorry, currently my wings are too tired to carry you much beyond that, but one day I will for sure. Our home planet is the third planet from the Sun and the only place we know of so far that is inhabited by living things. Apart from the small fact that it harbors life, there is nothing much that the Earth differs from other inner planets. Apart from this small fact, we are as significant as any other rock in this universe. While Earth is only the fifth largest planet in the solar system, it is the only world in our solar system with liquid water on the surface. Well, based on what we know today, of course. So we have classified Earth to be in a circumstellar habitable zone. It is also called the Goldilocks zone after the popular children's fairy tale of Goldilocks and the Three Bears. For those who are not familiar with the story, it is a fairy tale in which a little girl chooses from sets of three things, ignoring the ones that are too extreme like large or small, hot or cold, etc., and settling on the one in the middle, which is just right. The habitable zone is the area around a star where it is not too hot and not too cold for liquid water to exist on the surface of surrounding planets. Imagine if Earth was where Pluto is, the Sun would barely be visible, maybe about the size of a pea, and the Earth's ocean and much of its atmosphere would freeze. On the other hand, if Earth took Mercury's place, it would be too close to the Sun and its water would form a steam atmosphere quickly boiling off. The distance Earth orbits the Sun is just right for water to remain a liquid. The distance from the Sun is called the habitable zone or the Goldilocks zone. Rocky exoplanets found in the habitable zones of their stars are more likely targets for detecting liquid water on their surfaces. Just slightly larger than nearby Venus, Earth is the biggest of the four planets closest to the Sun, all of which are made of rock and metal. Earth has a very hospitable temperature and mix of chemicals that made life abundant here. Earth's vast oceans provided a convenient place for life to begin about 3.8 billion years ago. But before we start to discuss about how life began, shouldn't we be looking at how Earth began? When the solar system settled into its current layout about 4.5 billion years ago, Earth formed when gravity pulled swirling gas and dust in to become the third planet from the Sun. It was formed by a process called accretion, a disc-shaped mass of dust and gas left over from the formation of the Sun, which also created the rest of the solar system. Like its fellow terrestrial planets, Earth has a central core, a rocky mantle, and a solid crust. When the Earth was formed, it wasn't anything like what we see today with its flowing rivers and flowering trees with birds chirping on its branches. Earth was initially molten due to extreme volcanism and frequent collisions with other bodies. As time passed and as Earth continued to spin on its axis, the molten gases slowly began to cool. Eventually, the outer layer of the planet cooled to form a solid crust when water began accumulating in the atmosphere. Condensing water vapor held by the ice delivered from comets produced the oceans. However, more recently in August 2020, researchers reported that sufficient water to fill the oceans may have always been on the Earth since the beginning of the planet's formation. Another notable omission was that when the Earth was formed, there was no moon. And that was primarily because, as I mentioned in the previous video, the size difference between Earth and the moon is a big exception. To maintain a satellite which is a quarter of its size in its rotational orbit is not an easy task even for a planet the size of Earth. But at some point, an object, we don't know for certain what, collided with Earth. Theia is a hypothesized ancient planet in the early solar system that, according to the giant impact hypothesis, collided with the early Earth around 4.5 billion years ago, with some of the resulting ejected debris gathering to form the Moon. In addition to explaining Earth's large satellite, the Theia hypothesis can also explain why Earth's core is larger than would be expected for a body its size. Theia's core and mantle mixed with Earth's core and mantle. Additional evidence published in 2019 suggests that Theia might have been formed in the outer solar system rather than the inner solar system, and that much of Earth's water originated on Theia. How do we know all this? The lunar rock samples retrieved by Apollo astronauts were found to be very similar in comparison to Earth's crust, and so were likely removed from Earth in some violent event. Coming back to Earth, let us see what happened when Earth started to cool down. Why did the crust cool down first? Well, that is the layer which is lying at the very top, and hence it can dissipate energy to the outside space far more than its insides. Now, as the Earth's top layer cooled down, it solidified to form the crust. Now, since it is thick, it will prevent further dissipation of energy from within. So the inside of the Earth, called its core, is still in the state that it was 4.5 billion years ago. Above that is the mantle. Now, as you know, when anything solidifies fast, there are chances of cracks to appear. If you have watched people constructing houses, you would know that after you pour concrete and it starts to solidify, you wet it with lots of water. That is done to prevent cracks from appearing on the concrete as it solidifies. But when the Earth was formed, there was no one to water it, so there are many cracks in the upper crust. They move on top of the liquid mantle below. We call them tectonic plates. These plates slide over one another, may hit against each other, slide against one another, and they are all part of the game. So if there is a less dense portion of the crust somewhere, then the liquid mantle below rushes out, and we call it volcanic eruptions. So the initial phase of the young Earth was very violent in nature. One part cools down, molten lava flows up through the cracks on the surface, smaller elements such as hydrogen and helium gets blown away, but heavier elements like carbon dioxide, methane can hang around. So the first atmosphere of hydrogen and helium got blown away by the solar winds and got replaced with the second atmosphere of carbon dioxide and methane. The gases which are not part of the crust but gets accumulated around the denser core due to its gravity is what we call as its atmosphere. We now know that the Earth has had three different types of atmosphere. A first atmosphere of hydrogen and helium which were formed as the Earth first formed. This got blown away by the solar winds and were replaced by the heavier carbon dioxide and methane type of gases. This was a time when life actually originated on this planet. But there was a problem. This atmosphere caused by volcanic eruptions did not last long, and the eruptions started to slow down. At that time, cyanobacteria which had been formed started to make oxygen. During that time, the Earth's atmosphere was primarily carbon dioxide with very less oxygen. As the cyanobacteria started to release more and more oxygen, organisms which depended on anaerobic respiration, which is respiration using other elements other than oxygen, started to feel suffocated. Imagine a period where living things started to die out due to excess oxygen. We feel suffocated when there is no oxygen, but those days the living beings suffocated due to oxygen. This happened around 2.5 billion years ago, and we call this event as the giant oxidation event or an oxygen holocaust. The rise in oxygen is attributed to photosynthesis by cyanobacteria, which are thought to have been evolved as early as 3.5 billion years ago, and this enabled the subsequent development of multicellular life forms. Life started to evolve again in the third atmosphere, which had a higher concentration of oxygen but dominated by nitrogen, while carbon dioxide depleted to less than 1% of the total air. We are descendants of those organisms which thrived in an oxygen-rich atmosphere. But one need to realize that we are standing on top of the graves of billions of organisms which used carbon dioxide and methane to carry out their respiration process and survive. Now let us discuss a bit about the interior of the Earth. The innermost part of the Earth, called its core, is a highly pressurized region. The core is made of two layers, the outer core, which borders the mantle, and the inner core. The boundary separating these regions is called the Bullen discontinuity. The core is found about 2,900 kilometers below the Earth's surface and has a radius of about 7,000 kilometers. The primary contributors to heat in the core are the decay of radioactive elements, leftover heat from planetary formation, and heat released as the liquid outer core solidifies near its boundary with the inner core. The core is made up almost entirely of metal, specifically iron and nickel. It also contains a lot of precious metals called the siderophiles, which are more commonly called gold, platinum, and cobalt. In fact, one geoscientist calculated that there are 1.6 quadrillion tons of gold in the core. Yes, you are sitting atop a huge gold mine. But before you take your shovel and start to dig, listen to the rest of the video. Another key element in Earth's core is sulfur. In fact, 90% of the sulfur on Earth is found in the core. Although we know that the core is the hottest part of our planet, its precise temperature is difficult to determine. In general, temperatures range from about 4,400 Celsius to about 6,000 degrees Celsius. The outer core, about 2,200 kilometers thick, is mostly composed of liquid iron and nickel. It is the site of violent convection. The churning metal of the outer core creates and sustains Earth's magnetic field. The hottest part of the core is actually the Bullen discontinuity, where temperatures reach 6,000 degrees centigrade, as hot as the surface of the sun. The temperature of the inner core is far above the melting point of iron. However, unlike the outer core, the inner core is not liquid or even molten. The inner core's intense pressure, the entire rest of the planet and its atmosphere, prevents the iron from melting. The pressure and density are simply too great for the iron atoms to move into a liquid state. So the inner core is in a form where it thinks it is a fluid, but in reality it is not completely a fluid. It cannot flow like a fluid. You can equate it to the caramel that you see inside chocolate eclairs. The liquid outer core separates the inner core from the rest of the Earth, and as a result, the inner core rotates a little differently than the rest of the planet. It rotates eastward like the surface, but it's a little faster, making an extra rotation about every 1,000 years. Which brings us to yet another important question. Why does the Earth, as well as the other planets and the Sun and the entire solar system, spin? Though it is a bit complex, I shall attempt to do so in as simple a manner as possible. The physics behind it is a law called the law of conservation of angular momentum. It is a property of rotating objects. Before we get into angular momentum, let's consider momentum, which is easier to understand. Consider a car traveling towards you. The impact that you would feel when it makes contact with you depends on two things: how much mass does the object contain, and the speed at which it is approaching you. This is called the momentum of the car, its weight multiplied by its velocity. Now, instead of a car, consider a spinning object. Let us say a door slamming shut due to the wind. Here we need to consider the angular momentum. The more angular momentum, the more impact it would cause. Now the crucial fact is that you cannot remove this angular momentum. Similar as we say that energy cannot be destroyed but can only be transferred from one place to another, similarly the angular momentum can only be transferred. This is what we call the conservation of angular momentum. All the particles in the nebulae has this angular momentum. When they join together to form a bigger object, the angular momentum cannot disappear. They might not be able to spin on its own, but due to the combined angular momentum of the individual particles, the entire object begins to spin. As more and more objects become part of it, the angular momentum of the individual particles transfer the individual angular momentum to the whole object, and that is why all celestial bodies continue to spin. Now, why do they continue to spin? Our planets have continued spinning because of inertia. In the vacuum of space, spinning objects maintain their momentum and direction, their spin, because no external forces have been applied to stop them. And so the world and the rest of the planets in our solar system keep spinning and will continue to spin. In our solar system, the giant gas planets Jupiter, Saturn, Uranus and Neptune spin more rapidly on their axis than the inner planets do and possess most of the system's angular momentum. The Sun itself rotates slowly, only once a month. The planets all revolve around the Sun in the same direction and in virtually the same plane. In addition, they all rotate in the same general direction with the exceptions of Venus and Uranus. These differences are believed to stem from collisions that occurred late in the planet's formation. So coming back to planetary systems, all the stars and planets stay in place as a group of stars and planets due to the force of gravity working on them. We call such groups as galaxies. As you may all know, we belong to a galaxy called the Milky Way galaxy. As on 2021, the number of known galaxies in this universe is roughly 200 billion. That is 2 followed by 11 zeros. And we are just part of it in Milky Way, which has a diameter of 100,000 light years. That means for light traveling at a constant speed of 300,000 or 3 lakh kilometers per second, it would take light 100,000 or 1 lakh years to travel from one edge to the other edge through its center. Cosmologists group several such galaxies into a cluster and call it galaxy groups. The Milky Way is part of a galaxy group called the local group. Many such galaxy groups are combined to form a galaxy supercluster, and we are part of a supercluster called the Virgo supercluster, which again is part of a larger supercluster called the Laniakea supercluster. This is a picture of the Laniakea supercluster, and in this we won't be able to spot our galaxy. Forget spotting Earth. We are paler than the pale blue dot from this distance. We estimate that there may be 40,000 crore stars in the Milky Way and around 100 billion planets, and we have 200 billion similar galaxies, and the number of superclusters in the observable universe is estimated to be 10 million. Don't bother trying to compute these numbers, your brain would get short-circuited. And yet we, puny little primates sitting on a planet smaller than a speck of dust within this grand universe, think that the entire universe was created by some sky daddy sitting above all this for us, and throw our weight and ego around thinking that we are something of importance in the whole system. It is when you get the real feel of the universe we really understand the true sense of how insignificant we really are in this world, and that knowledge, that modesty will enable us to treat each other with more respect, treat our only home with much more care, and preserve and cherish the pale blue dot, the only home that we have. So I hope you enjoyed the bird's eye view of a solar system and you got a feel about our home and its neighborhood. Of course, there are plenty more to discuss, and as long as the solar system is there and I am there, we will continue to discuss. There are a few more things that you might want to hear, like the beginnings of the universe, are we alone in the universe, the Big Bang Theory, abiogenesis, the start of life on Earth, and evolution by natural selection, the means of explaining how there is diverse life on this planet, and so many other things. To learn about that, you will need to click on subscribe and click on the bell icon next to it so that you will be notified whenever I release new videos. So join me another time when we will discuss the universe in detail. Until that time, it's bye-bye from Pale Blue Thoughts.